So as we discussed about the GRBs and their observational evidences that they are cosmological evidence and that they are isotropically distributed, based on that, a large number of the statistics of GRBs indicate that some of the GRBs are they have duration less than 2 seconds, and the majority of GRBs they have a duration more than 2 seconds. So this bimodality is a clear-cut evidence that there are short duration bursts and long duration bursts, and their hardness distribution is also an evidence which says that short, hard, and long, soft class of bursts exist, and that way this is an evidence that probably they have a different class of progenitors also which are responsible behind this modality. But still we need to understand a lot more because there is an intermediate class of population which also exists. Along with these evidences and with the evidences of the GRB supernova connection and that some GRBs they don't radiate in gamma rays but in X-rays, that's called X-ray rich or X-ray flashes, we need to understand if there is any possible continuum among these class of bursts, and that will tell a lot more about the nature of the progenitors and their implications. So, apart from these information, nowadays we have many other dedicated satellites which are working to know more about these gamma ray bursts, and one such very successful mission is called SWIFT, which has been launched in 2004, and it has onboard X-ray telescope, gamma ray telescope, and optical UV telescope. So BAT is known as Burst Alert Telescope, which localizes, it's a wide field camera which localizes the GRB with an order of accuracy of half minutes. And XRT is another instrument working in 0.2 to 10 kV which can localize these GRBs in an energy range. It can precisely localize with an accuracy of arcsecond, and a sub-arcsecond localization can be further done by UV telescope and a possible optical control. So with these telescopes, we have been able to decipher many properties of these GRBs, and if you see the light curve which have been obtained from these telescopes, then we see that next slide. We see that if you see this light curve, the black light curve is the X-ray light curve, and the red light curve is the possible optical light curve. They don't match with each other. So a very fundamental thing is that if the source of these emission are same and the underlying physical mechanism is same, then they should track each other, but they don't track each other, and that's where we get a piece of information about the progenitor model and the underlying physical mechanism about these sources. The SWIFT has been able to decipher many of the questions which were earlier, as well as it has raised some new questions which are really unknown. Another new mission which have been able to put some new questions and has been able to answer a few of the unsolved questions is Fermi. Fermi was launched in 2008, and it has onboard a large area telescope called LAT, which have been able to detect GRBs in the GV energy range, and the GBM gamma ray burst monitor, it has been able to observe gamma ray energy range. So GBM is a wide field and the LAT is relatively narrow field camera, and the LAT follows the principle which we have been used in CGRO onboard E-grade. It's a pair convergent telescope, and the LAT has shown that we are able to detect some 10 to 12 GRBs per year with LAT, whereas more than 250 GRBs have been observed every year by GBM. But the less number of LAT detected GRBs put a lot of constraints on the progenitor models as well as the nature of high energy emissions. So if we see in the upper portion of this figure, we have a spectralized distribution of the burst spectrum, where the green line shows the power law, double broken power law model, and we know the question mark, so that at very high energy, that is at GeV, we still do not know whether there is a cutoff at very high energy ends, or it's going up, or it follows the same power law which has been continued at higher energy. This piece of information is definitely useful to constrain the spectrum of the burst, and that's how the nature of the progenitor and what kind of physical mechanism is underlying. If you see the next slide, then some of the Fermi results, and these are the examples where Fermi have been able to detect the GV emission, and this GV emission in the red, it's a very important and interesting GRV. It's a short duration GRV called 090510, and this GRV have been able to see that the high energy radiation is actually dominating not only in long duration GRV but in short duration GRV as well. And this is the spectral energy distribution of the GRV, of very energetic GRV O called GRV 080916C, where the GVM energy it looks like that it's an extension of the simple power model of the low energy emission, and it doesn't show any specific enhancement in the flux, which can really have been predicted by different other models. So, so one detection per month is the rate of one lab, and no GV access has been seen in most of the GRBs. But GV emission has no access, but it has been seen in a fraction of GRB. And another important thing is that this GV emission has been detected both in long duration GRBs as well as short duration. Next. So the lat emission, as you can see here, the red dotted line, the horizontal line is the starting of the burst. The green and blue channels are different energy channels of this GVM detectors, but the lower panel, the red light curve indicates the lat detected photons, and if you see, then these are detected, but they have been detected and they are rather delayed. This delayed emission, and the reason behind this delayed emission is rather unknown, and different physical mechanisms, hadronic modules and so on have been predicted, predicted and have been made to understand this delayed emission, but the exact reason behind these kind of delayed emission is still unknown. So to summarize it, since very beginning, if you see, the dark era was from 73 to 91 when discovery was made by Gladstone and et al. In 73. Then Batse era came from 1992 to 1996, where it was established that the distribution of these GRBs are really uniform, and their special distribution indicated that their cosmological detection rate was also established. And the Mappisax era was a real revolutionary era when between 1997 to 2000, many afterglows were discovered, redshifts were measured. That was clearly established. That clearly established that actually these GRBs are cosmological in medicine. 82 was another satellite, meanwhile, which gave rise to GRB supernova connection, and spectroscopically type 1 BC supernova were discovered, which were associated with the GRB. And then, as we discussed earlier, from 2005 onwards, many early afterglow features and short duration GRBs and higher GRBs were discovered from 2005 and onwards. And that's how GRB cosmology came into picture, that if at all these energetics are standard, then these sources can be established and can be used for cosmological implications. Next slide.